All right, so VPNs, let's get into it then. So the first thing that I want to take a look at is the concept of a VPN. What is a VPN? First thing you need to understand is a VPN does not mean encryption. Because one of the first things that comes to mind when we talk about the word VPN is that it's a secure tunnel or it's an encrypted tunnel. That's wrong. What the definition of a VPN is to connect two private networks over a public network. And the public network could be your service provider, or it could be your internet service provider. For example, let's say you're doing a private WAN using some type of technology that the service provider is providing, like what? MPLS VPN, maybe VPLS, maybe Q&Q tunneling, even frame relay, if you still have it. And these are two sites that I have, let's say in LA and in New York. I want to connect them up. I already have my service provider connecting the two sites to each other by using any of these technologies. This is a VPN. This is a private WAN. This is a VPN, virtual private network. None of these technologies that I mentioned over here are encrypting technologies. When you send the traffic from LA to New York, you're going over a service provider network that has other customers here. The job of the service provider is to make sure your network or your traffic does not get mixed up with the traffic of other customers. That's what a VPN provides, virtual private network. It's all clear text. Okay, clear so far? If I want to encrypt this, I would need to run an encrypting technology, but that's a recommended thing, not a required thing. What are these type of VPNs called? This one, as the name suggests, MPLS VPN. These type of VPNs, because their forwarding of the traffic through the service provider cloud is done using a layer 2 technology, these type of VPNs are referred to as layer 2 VPNs. Generally, when you look at frame relay, you don't look at it from a perspective of what? A VPN, but frame relay is a VPN. VPLS, Q&Q tunneling, all VPN technologies. They're all layer 2 VPNs because the forwarding of the packet through the service provider network is done through layer 2 headers. Whereas with MPLS VPN, it's forwarded based on label. So that's why it's called MPLS, label switching VPN. Good so far, guys? Everybody okay with that? The other type of VPN that you have is an IP-based VPN. And that's the one that we'll focus on in this particular class. Not so much on the other type of VPNs, the layer 2 VPNs. Our focus is going to be, let's say this is an ISP now. This is the internet. My LA office is connected to the internet. It has a public address. The New York office is connected to the internet. It has a public address. I have the ability, by using encapsulation, to take a private packet, which has a private address, connected to my private network on the other side by virtue of encapsulation. What I'll do in that type of VPN is I'm going to take the internal packet, which is 10.1.1.1, for example, going to 10.2.2.2 with some data on it. And what I'm going to do is I am going to encapsulate it with a public header. The public address will be the the public address of the LA router, the internet routable address, with the destination of the public address of New York, again, the internet routable address. So let's say these addresses are 199 in LA and 200 in New York. So what I've done is I've taken this entire packet over here, treated as data, encapsulated within an outer header. It has the public addresses. Good so far, guys? This is also a VPN, but this time around, the forwarding of the packet through the internet is done through a layer through header. So this is known as a layer 3 VPN. Following along, guys, everybody okay with this? Now, what are the different protocols that are used for this type of VPN? The different protocols that can be used to set this up. You can have a protocol like GRE. Is that with everyone? My speed over here is good. Let me just make sure. Second. Alfred, maybe there's something wrong on your side though. That's more than enough. I mean, I can do it with 5 megabits per second. Let me check my upload. Give it a second. Speed should not be an issue here. Yeah, this is good enough. So maybe something wrong on your side, Alfred. So one of the protocols that is used to set this up is GRE. The problem with GRE, although it does the encapsulation, the data is sent in the clear, and we'll talk about that as well. So although it is sending the data across the internet, this data is clear, so you can actually use a sniffer and see this data. That's where IPsec is a more commonly used protocol on the internet to do this type of VPN because it does encrypt the data. There, everybody? You guys understand that? Yeah? So these are the two main protocols that we'll be taking a look at for VPN. We'll also take a look at another protocol for VPNs, more used for your remote access VPNs. Which is SSL. All right, those are the three main protocols that we'll be taking a look at in terms of VPNs over here. We'll take a look at GRE, IPsec, and SSL to set this VPN up. This is an overview of VPNs at this point. Good? Now, with this in mind, now let's get started with your, one second, guys. All right, so sorry about that. I just wanted to give some people the meeting ID. First thing we'll be taking a look at over here is a LAN-to-LAN VPN using cryptomaps. So I'm going to be using IPsec as a protocol over here to set up a VPN between two sites to encrypt the data. Okay, that's my objective over here. And in terms of coverage, where are we at and what am I talking about right now? This point, I'm going to be focusing on this thing over here. All right, clear? So let's go through a real quick overview of IPsec and encryption in general. So in this particular section over here, we're going to be taking a look at what encryption is all about, basic overview of encryption. We'll take a look at IPsec overview, and then we'll set up a LAN-to-LAN tunnel using IPsec. Although this is very basic, this sets up the format of how IPsec runs for more advanced VPNs like DMVPN, like GetVPN, FlexVPN. Everything will be based on these basic elements that I'm going to be using over and over again in the other type of VPNs. So to start with, let's take a look at encryption as a very simple format. I don't want you guys to get into the actual algorithms of how the encryption works, because for you, unless you're rewriting a protocol or an operating system, those algorithms really you don't really care about them. You need to know the actual implementation of those algorithms. But just to give you an idea of what these algorithms are doing is this. If I want to exchange some data from router 1 to router 2 over here to a tunnel, and I want to make sure the guy in the middle does not understand what data I'm sending, I set up each side with a encryption key, a very simple format. This is a very simple illustration of how encryption works. Both sides have a common key that they know about, that in this key, which is the encryption decryption key, I have agreed upon that A is going to be equal to 1, B is 2, C is 3, D is 4, so on and so forth. If both the entities have agreed upon that, now that they know that they're doing encryption, for R1 to send some data to R2, let's say he wants to send the data feed, he's going to send the word 6, which is FEE4. The guy in the middle will see it as a normal number. Say the guys are just transmitting some arbitrary number. He gets 6554. He decrypts it and says, oh, 6 actually stands for F. 5 stands for E. 5 stands for E. 4 stands for D. So he's trying to send me the word feed. He wants to send him the word dead. He would send in D, which is 4, E, which is 5, A, and D. 4514, and the guy in the middle just again sees the number 4514, but the other guy knows it's dead. Everybody okay with that? Very basic form of encryption, but that's what encryption does. So bottom line that I want you guys to understand over here, that both sides need to have a key to be able to decrypt and encrypt the data. So whatever you encrypt, I need to have the same key on the other side to decrypt it. The problem with this type of setup is if I keep on sending a lot of data, using the same key, the guy in the middle can collect that lot of data and run it through an attack, a very commonly known attack known as the brute force dictionary attack. In this particular attack, what it does is it takes a lot of data. But again, the key is I need to have a lot of data, and runs different combinations. It's a computer program that will run different combinations and look for different patterns. In the patterns, it will match every character and try to match it with a word in the dictionary. Look at for different combinations, like a crossword puzzle type of thing. The only difference is the computer is doing it one character at a time. And I'll find out that every time it sees the number 5, it sees it used in conjunction where it matches a word in the dictionary, which is an E. Whenever it sees the number 4, it matches with the alphabet D. All right? Because it's tried it with different combinations and it figures out that, oh, A is 1, B is 2, C is 3, D is 4, and reverse engineers and figures out that this is the key that these people are using to encrypt the data. And what was required to set that up? What was required for me to be able to compromise the key for the two users? What's a basic requirement of decrypting it? A lot of data. Understand? So my premise of the whole thing is a lot of data collected using the same key can compromise the key. So how do I get around that? The way you get around that is by changing the key on a regular basis. If you keep the same key on a regular basis and generate a lot of data using the same key, you have a chance of generating too much data using the same key where the guy in the middle can basically crack the key by running it through the brute force dictionary attack. And that's what I explained to you guys in this particular slide over here. A common key which exists on both sides is used to encrypt and decrypt the data. Move this to the side a bit. Okay. If the same key is used to send a lot of data, the intruder in the middle can collect the data and run it against the brute force dictionary attack to reverse engineer the key by matching the combination of the characters with words in the dictionary. Everybody okay with that? The question, can the guy in the middle take the prior data and brute force past data? No, because as long as your keys are generated from scratch, they can. If your keys are generated based on older keys, that is true. So one of the things that you can do is you can use a mechanism in IPsec known as a perfect forward secrecy, PFS, in which the new key is generated from scratch. So if it's generated from scratch, it is going to be protected against that. All right, but that's an option. Otherwise, again, it's very tough. Even if you're changing the key, it is not going to be something that's going to be an issue. So what do they do for that? How do they fix that problem? The way they fix that problem, and what I've done over here for this is I got my whiteboard over here. What they do for that is they have a mechanism. The job of the mechanism is to generate a new key, a dynamic key. Mechanism for dynamically generating a key. And what is that mechanism called? It's called the Diffie-Hellman mechanism. Okay, what does Diffie-Hellman do? The only job that Diffie-Hellman has on a regular basis, wake up and generate a new key. The default lifetime of Diffie-Hellman to generate a key, the lifetime of a key is 3,600 seconds. Okay, that's basically 1 hour. So the job of Diffie-Hellman is to generate a new session key, the key that will be used for that particular session. The session is valid for what? 1 hour. When you generate the Diffie-Hellman key, you need to specify the size of the key. How secure do you want to make the key? More secure that you make the key, more time it will take the router to encrypt and decrypt. Okay, so you need to strike a balance between security and what do you call it? Security versus performance. Is that the same protocol that RSA uses? No, RSA is a little different. Diffie-Hellman is generic. You can use Diffie-Hellman without RSA. RSA uses a different mechanism for its public-private key. So You guys understand what the purpose of Diffie-Hellman is. So for example, you can generate a Diffie-Hellman key, which is 768 bits in size versus 1024 bits in size versus 1536 bits in size, and so on and so forth. Each one, this is low security, let's say high security, medium security, depending on what level of security you want and what is a trade-off in terms of security versus performance. That depends on the type of implementation that you're doing. Good so far? Now you have two entities at this point. Each one would have generated its own key. This key that Diffie-Hellman generates is known as the session key. So router 1 would generate a session key. Let's call it session key number 1. Router 2 independently, Diffie-Hellman will come in over here and generate his own session key. Good so far, guys? So router 1 will use session key 1 to encrypt the data and send it to router 2. Router 2 will use session key 2 to encrypt the data towards R1. But there's a problem. Remember, if I encrypt something with session key 1, what do I need to decrypt it on router 2? I need the same key. So once the key is generated, what's going to happen is I'm going to encrypt from router 1 to router 2. I'm going to use session key 1 to encrypt. And going this way, I'm going to use session key number 2, which is this guy generated locally on R2 to encrypt. You guys following so far? Is that an issue? Yes, there is an issue because router 2 has no idea what session key 1 is. Router 1 has no idea of what session key 2 is, so it can decrypt. You get my point? So what they did was they wanted to set up a secure tunnel to exchange the session key with each other. Because R1 is generating the key independently, R2 is generating the key independently. This key is going to be used for data encryption. But the problem, again, as I said, is this key is independently generated. So as Trent says, how does it get the key to decrypt? So what I need to do over here is I need to create a separate tunnel, a secure tunnel. This secure tunnel will be used to exchange the session key. Good so far, guys? Now, this session key that will be exchanged through the secure tunnel requires certain parameters. To exchange, or I shouldn't say that, to set up a secure tunnel, any secure tunnel, I need 3 parameters. I need an encryption key, I need an algorithm for encryption, and I need a hashing algorithm. Hashing makes sure the data is not tampered with. The same parameters need to exist on the other side. So to set up a secure tunnel, I need 3 parameters. What are the 3 parameters that are required to set this tunnel up? Key, encryption, and hash. Key, encryption, and hash. The encryption algorithms that you have access to, You have DES, triple DES, and AES. A choice between the three, again, low, medium, and high. In terms of your hashing algorithm, hashing is like a checksum. It doesn't encrypt, it just makes sure the data is not tampered with. Two main algorithms for that, MD5 and hash, or MD5 and SHA. So if I'm specifying my encryption algorithm over here to be triple DES on this tunnel, and this is something that is negotiated manually between the administrators of the two routers, they will set the encryption algorithm of the secure tunnel to be triple DES, and my hashing algorithm, I'll send that to be, let's say, MD5. How about the key for the secure tunnel that will be used to exchange the key? I can set this key for right now manually. This manual key is known as a pre-shared key. Okay? The pre-shared key, which basically means that administrators of the two endpoints will call each other WhatsApp, Facebook Messenger, email, whatever mechanism. They will agree upon a common key that will be used, manually agreed upon between the two entities to encrypt this tunnel, like a password. So what I'm going to do over here, manually, on the two sides, I am going to set up a manual key, which is known as a pre-shared key. For example, Cisco. And over here, manually, I'm going to set the first key to Cisco. This is what is required to set up a secure tunnel. What is required? A key, encryption, and a hash. Understood, guys? Once the tunnel is established, Mike, what Diffie-Hellman will do is it will generate that session key. You get my point? So the purpose of Diffie-Hellman over here is not to set the secure tunnel up. The purpose of Diffie-Hellman is to generate the session key that will be exchanged over this secure tunnel. So the only parameters that I need to set the secure tunnel is key, encryption, and hash. Get my point? So the actual thing that I'm setting this secure tunnel for is the exchange of the session key. Remember the session key 1 from this side, session key 2 from the other side. Understood, Mike? So Diffie-Hellman, yes, I need to set it up in this particular setup, but it's not to set the secure tunnel up. The secure tunnel is set up to exchange the Diffie-Hellman generated session key. Got it? So just to write or draw that again for you guys, in order to set my secure tunnel, I will generate using Diffie-Hellman a session key. Session key 1, this guy using Diffie-Hellman will generate the session key over here, let's say session key 2. I need to set up a secure tunnel between the two sites so that I can securely exchange that session key. In order to set up a secure tunnel, I need a key, encryption, and a hash mechanism. Key is going to be set up manually. This is known as the pre-shared key. Later on in the course, I'm also going to show you how to do it based on the RSA public-private keys. For right now, let's stick to the pre-shared key. Okay? Once this tunnel is established, what is exchanged within the secure tunnel? It's the exchange of the session key this way, session key the other way. Good so far. What's the end result of this particular exchange? I had my own key already over here, which was session key 1. This I'm going to use for encryption. He had set up what? Session key 2, which was Diffie-Hellman generated. He's going to use that for encryption. But at the same time, using this exchange, now I have received what? Session key 2. Trent, remember your question? How does the other guy know about the session key? That's exactly what I did over here. Now I can use this to decrypt it. He encrypts it, and this is done using, it's decrypted using session key 2. And similarly over here, I'll have session key 1 that will be used to decrypt the data that was sent from the other side. So these keys, key, encryption, and hash, are all phase 1 elements for right now, Marvin. Every secure tunnel will require key, encryption, and a hash. Every tunnel. For right now, what I've done is shown you how to do my first tunnel. The first tunnel, the job of the first tunnel is to do what? Exchange the session key. That's it. So there's no data going across over here. It doesn't, so Diffie-Hellman gets the decrypt key, no. So Diffie-Hellman generates its own what? Session key, that's all it does. So Diffie-Hellman will generate his session key. Diffie-Hellman over here will generate his own session key, that's it. Diffie-Hellman is done. Okay, now I need to send my session key to the other side. I need to send session key 2 on router 2 towards R1. To exchange that securely, I need to set up a secure tunnel. Good so far, Trent? Now, to set the secure tunnel up, I need 3 parameters to secure the tunnel. I need a key, encryption, and a hash. And that statement, to secure a tunnel or create a secure tunnel, I need those 3 parameters regardless. Key, encryption, and hash. So I'm setting up a secure tunnel by specifying the pre-shared key to encrypt it, encryption algorithm, and a hashing algorithm. So once the secure tunnel is established, the key that was generated by Diffie-Hellman is exchanged. Does that clear it up? So one of the things that you can say is the pre-shared key was used to encrypt the session key. The pre-shared key was used to encrypt the session key when it sent it across to the other side. Everybody following so far? What's the end result of this particular tunnel? What has happened at this tunnel as this process completes? The 2 guys have each other's session key. Now I'm ready to exchange the data. Now, in order to exchange the data, I still need a secure tunnel. And what have I been talking about in terms of securing a tunnel? What parameters do I need to secure the tunnel? Any tunnel. Key, encryption, and hash. Key, encryption, and hash. The key part of it is done. That was the whole purpose of the first tunnel. What did the first tunnel do? The only thing that the first tunnel did was to exchange the session key. So my key part for my second tunnel is done. But I still need what? To complete the parameters for my secure tunnel. What do I need to define for my second tunnel? I don't need to define the session key or the key because that's already done. I need the encryption and the hash. So again, I need to define what? The encryption parameters and the hash parameters that needs to match the other side. So let's say I want to do triple des over here. And I want to do SHA as my hash. Triple des over here has to match, and SHA over here. So again, 3 parameters to set up the secure tunnel as well. But over here, the actual data will go across. You understand that? So the purpose of the first tunnel is just to provide the session key that will be used as the encryption key for my second tunnel. Tell me if you guys are okay with this. Any confusion in terms of this? This one, I want you guys input. So make sure that everybody's on the same page over there. All right, now the protocols that are used. To set my first tunnel up, I use, which is by the way called phase one. The protocol used for the first tunnel is a protocol by the name of ISACAM, also referred to as IKE. It works on UDP port 500. So phase one, or the ISACAM tunnel, is used just for the exchanging of what? The session key. Once the session key is exchanged, I use the session key as the key for my second secure tunnel, which is for the data encryption. Again, for every secure tunnel, I need three parameters: the key, the encryption, and the hash. I already have the key. That was the purpose of phase one. Now I'm into phase two. Phase two is where my data encryption takes place. Okay. This is done by a protocol known as ESP. This is protocol, it's its own protocol, protocol 50. It doesn't work on UDP or TCP, it is its own protocol at layer 3. Protocol 50. That's ESP. Now, what happens after this session key expires? How long is the session key valid for by default? 3,600 seconds, 1 hour. What happens when this key expires? Diffie-Hellman wakes up again, generates a new session key, it changes it again, goes back to sleep. So this tunnel will only be used once an hour, once an hour. It changes it, goes back to sleep. So most of the time, phase one will be in what state? Idle state, because it's sleeping. His job is top of the hour, wake up, generate a new key, exchange it, go back to sleep. That session key keeps on changing for now too. So that way, that a lot of data that I'm generating, it will keep, the key will keep on changing, so it'll be tougher for them to crack the key. Everybody okay with this? Okay, let me show you the illustration of this real quick. So this Diffie-Hellman generation of this Diffie-Hellman key, the default on a Cisco router is every 3,600 seconds. The Diffie-Hellman protocol will generate a new key. The key exchange will be done through this secure tunnel. In order to set up a secure tunnel, what are the three parameters that I told you that you need? A key, which is a pre-shared key, needs to match on both sides. Encryption algorithm for making sure the data is protected, scrambled, and hash to make sure the data integrity is maintained, no changes happening. The protocol used for this tunnel is UDP 500. So all that is in your slide. I'll provide these slides as well as part of the course. Now I'm ready for data encryption. Now data encryption tunnel that you have, which is called phase two. This is where the data goes. Once the keys are generated, I have that session key exchanged. A new tunnel will be needed to be set up for the data encryption. Again, I need a key, encryption, and a hash. The key part is done, which came in from phase one. I just need to define the encryption and the hash. The key used for this tunnel is the dynamically generated tunnel that was exchanged in the first tunnel. You need to define the encryption and the hash. The protocol is 50. All good? So I'm just reviewing what we talked about. The graphic illustration of this is here. This, take a look at it. Take 15 seconds, 20 seconds. See if you understand this graphic right now. Absolutely correct, Trent. Absolutely correct. They always will be up at the same time. This will be an idle because his job is to do what? His job is to change the key at the top of the hour and then go back to sleep. It'll be up, but it'll be in the idle state. Got that, Oscar? He'll wake up at the top of the hour when this key is expiring and generate a new key. Now, let me tell you another thing, which is not recommended. What was the purpose of phase one over here, ISACM? To exchange this Diffie-Hellman generated key in a secure manner. If I want, I'm not saying I would recommend that. If you want, I can set the key for encryption manually as well. If I do that, do I need phase one then? If I manually set the session key, I do have the capability of doing it. If I do that, do I need phase one? No. So phase one is not a required thing. If I'm doing the session key manually, I don't need to set up ISACM or phase one. What's the drawback of doing it like this? That means I'm manually setting the key. There's no lifetime on it. That means I'm going to change a lot of data using the same key. And that is where the compromise could potentially take place. So the PSK decrypts all the keys that are generated every hour, correct. But that, again, and that can be decrypted by the PSK, or does the PSK just decrypt? No, the PSK is used to encrypt and decrypt the first phase. So all the keys that will be exchanged over the first phase, not just one key, all the concurrent key, the keys that will be coming in later on, they're all encrypted using the same pre-shared key. You might be alluding to the fact that there's a lot of encryption that has taken place over here, but the key sizes are small, it's in bytes. So remember, you need a lot of data to crack the key. There's not a lot of data that's going over phase one. Does that answer your question, Trent? So it's the same pre-shared key that I'm using to exchange or secure all the session keys, not just today, tomorrow, day after. It's the same pre-shared key. So even if you change the pre-shared key after, let's say, 2 days or 3 days or 2 weeks, it really doesn't matter because there's not a lot of data that is exchanged using that pre-shared key. Now, the more secure way of doing it is using RSA keys rather than a pre-shared key, but this is also good. You don't have a mechanism to change the session key every hour. Yes, that's the drawback of doing what? A manual key. But what I want you guys to understand is that you do have the capability of generating or creating your session key manually as well. Correct. That is correct, man. Everybody on the same page right now. All right. Now, once this is done, the traffic, the two tunnels are set up. The next thing that I need to define is what traffic will be sent through this tunnel. I might have 5 networks over here internally in, let's say, LA. And I might have 2, 3 networks over here in New York. What networks are allowed to go through the tunnel? What networks should be encrypted? These are called the interesting traffic. This is called the interesting traffic. Traffic that needs to go through the tunnel. This is defined by a policy, essentially an ACL. So for example, if I had 10110 over here, 10120 over here, 10130 over here, and so on. These guys over here, 10210, 10220, 10230, and so on. I only want to encrypt traffic from, let's say, 10112, 10222. So I'll define that in my ACL, what traffic is interesting that needs to be sent across. Understood? That is done by creating what? The interesting traffic ACL. Got it so far, guys? Everybody understand that? So this is basically your basic LAN to LAN IP set. Questions, guys, at this point? Configurations, I'll show you, but the concept, I want you guys to understand. Now, let's go ahead and set this up. What I want to do, I have this network that I have set up. Very simple network. R3 is acting as the internet. It has 2 networks behind one. Let's say this is your LA router. And I have a New York router which has 2 internal networks. They have these as their public addresses. Okay? Clear so far? Router 1 can access router 2 publicly using 199.111 as its source, 200.111 as its destination. Let's take a look at this. This is my topology over here, router 1. Show IP interface brief. I have 3 networks of public, 199.111. These are my 2 internal networks. If I take a look at my routing table, I have a default gateway pointing to R3, which is acting as my internet, my networks, 10.1.1, 10.1.2, and the public network. Router 2, the other side, which is the New York router, 200 as a public, and these are 2 private networks that I have. All good so far? Again, my default gateway pointing to 200.113, which is again the internet. Ping 199.111, source 200.111. I can ping it. So over the internet, communication is working properly. All good so far? All right, brilliant. Now what I want to do is I want to take the traffic over here. I don't want to encrypt all the traffic. I just want to encrypt traffic from, let's say, 10.1.1 to 10.2.2, 10.2.1. Actually, let's do this. 10.1.1 to 10.2.2. This traffic needs to be encrypted securely over what? This tunnel network. How do I go about doing it? So my job, my objective over here is to do what? Lab number 1. What is a lab? Configuring a LAN to LAN IPsec tunnel between R1 and R2 to encrypt traffic between 10.1.1.0 and 10.2.2.0 behind the respective routers. That's my objective. Good so far? Now, how do I go about doing it? Whatever steps that I'll take over here, what I do is every configuration that I do, I break it down into small steps. So my first step over here is to configure my phase one. So I'm going to do this. I want to do this configuration on router one. I'm going to break it down into steps. First phase, step one is phase one. In phase one, I'm going to specify or define my ISACAMP parameters. How do I do it? What are the commands to do it? Crypto, ISACAMP, policy, and a sequence number. I can have multiple policies, different policies for different routers. Pick a number. By putting a number, a lower number, it gives that policy, that set of parameters, preference over another one. I'll explain that as well. For right now, it's just a number, like a sequence number in a route map. So over here, I need to specify the three parameters. What are the three parameters that I need? Remember the three parameters, guys, to set up any tunnel? What are the three parameters? Key, encryption, and a hash. So I'll say I'm using pre-shared key, and my key is Cisco 123. This key is going to be used when I communicate with this peer. So I'm tying up this key to this address. Whenever I communicate to 200.111, I'm on router 1, who's 199.111. When I communicate to 200, which is my peer, I want to use this as my key. So my key is done. What's the other parameter you guys said? Encryption, right? Encryption, let's use triple des. And the hash, right? Hash, let's say MD5. So at this point, what have I done? What have I accomplished by looking at this? I have a secure tunnel right now between what? R1 and R2 for phase one, using the protocol ISACAMP. I've defined key, encryption, and hash. I'll do the same thing on the other side. Okay. What was the purpose of phase one? I wanted Diffie-Hellman to generate the key and exchange it, right? So I need to define the size of your Diffie-Hellman, the key, the session key that I'm going to be generating. That is done based on a command called group. Group, you define the key size. You guys remember the low, medium, and high key? Group 1 will generate a key size of 768-bit. Group 2 will generate a key size of 1024-bit. Group 5 will generate a key size of 1536, and so on. But I'm going to use this guy. To generate the key. So this over here defines what? The key size for what? My session key. You understand every single parameter that I put in over here. You guys understand the significance of each command that you put in over here. All right, good. So that's the case. Let's move on to my second step. What's the end result over here? After I'm done with this phase, the session keys are exchanged. Right? Now I'm moving on to my second tunnel. Again, for the second tunnel, which is phase 2, which is my ESP parameters or tunnel 2 parameters. What do I need? Again, to secure a tunnel, what parameters do I need? This is phase 2 now. I do need the key, encryption, and hash, but the key portion is taken care of. Right? So I only need to define encryption and the hash. Why? The key is already done based on phase 1. So now I'll do crypto IPsec transform dash set. Give it a name, whatever you want to call it. ESET, transform set. ESP triple des, that's my encryption. ESP, let's say SHA, HMAC. That's your hashing algorithm. HMAC is a variant that your Cisco routers use. Most of the routers use that, the variant of SHA, the common variant of SHA. Good so far, guys? You understand what I did in the phase 2? I didn't specify any key in phase 2. Why not? Phase 1 generated my key. That's the one that I'm going to use in phase 2. I need to define my encryption, which is triple des, and my hash, which is SHA. I also want you guys to notice that on phase 1, what is my encryption and hash? Is it the same? My encryption over here is triple des. My hash over here is MD5. I did that on purpose. I want you guys to understand between the two tunnels, the two parameters, two sets of parameters don't need to match. I can use different parameters over here. As long as my peer tunnel parameters are the same. I need tunnel 1 to match tunnel 1. I need tunnel 2 to match tunnel 2. 1 and 2, they're independent. They can be the same. They can be different. It really doesn't matter. Okie doke. What I said over here was when I set the two tunnels up, I have two tunnels over here configured, phase 1 and phase 2. Phase 1 parameters need to match phase 1 parameters. Phase 2 parameters need to match phase 2 parameters. I don't really care. There's no connection between 1 and 2. So this could have been different. This is different. This could be the same. This could be the same. They're independent of each other. So just because I use triple des and MD5 on phase 1, I don't need to use triple des and MD5 for phase 2. They can be different parameters. Good, Oscar? There are two independent tunnels, by the way. Tunnel 1 is different, tunnel 2 is different. So it's not like one tunnel is carrying the other tunnel. Tunnel 1, phase 1, it was just used to generate the key that will be used for tunnel 2. But once that's done, tunnel 1 is sleeping now. Okay, so yes, tunnel 1 was used to generate the key for tunnel 2, but after it's generated that, for the next 1 hour, phase 1 is sleeping. Once that key expires, phase 1 wakes up again, generates a new tunnel, exchanges it, goes back to sleep. Tunnel 2 is now going to use a second key. So this key keeps on changing. So if somebody wants to hack in and take a look at the data, the key keeps on changing. Ben, got it? All right, now I'm done. My two tunnels are set. What was the third thing that I told you that you need to define after my two tunnels are up? Interesting traffic, which is also known as a crypto ACL. That is correct, Martin. That's why you see idle. And 99% of the time you'll see idle. You really need to hit the show crypto ISACamp SA command on the head to be able to see active. Otherwise, it's just going to be idle because it happens within a matter of milliseconds. The interesting traffic is an ACL. So what's my interesting traffic over here, guys? 10.1 going to 10.2. I'm on router 1, so my interesting traffic is defined by an ACL, permit IP 10.1.1.0, inverse mask 10.2.20, inverse mask. That's done. Now the thing over here is when I define these three steps, these are three independent steps, right? Where did I say this transform set will be used for this flow of traffic? I haven't done that. That is done in the next step over here for this IPsec tunnel, which is link the above parameters each other. This is done by using a crypto map component. So the purpose of the crypto map is to connect these steps to each other. This is a very important component because this is the one that is actually applied to the interface to tell it to encrypt or not encrypt. So the way you do that is crypto map, give it a name, whatever you want to call it, CMAP, crypto map, sequence number, any number. The reason you need a sequence number over here is on one interface. Let's say I had this as the internet. I have router 1 over here. I had other sites that I want to set up a VPN towards. This has 10.330 behind it. This guy has 10.220 behind it. And I have 10.110 behind it. Okay. I want to create a tunnel to encrypt traffic from 10.1 to 10.2, 10.1 to 10.3. Let's say the addresses that I have, my public addresses, let's say are 199.111. This is 200.111. Let's say this is 111.111. So I'm going to set up one tunnel which will be used to encrypt traffic from 10.1 to 10.2. And the peer for that would be 200.111 from my perspective. And I'll create another tunnel, another crypto map or crypto setting that will say if traffic is coming in from 10.1, interesting traffic going towards 10.3, set the tunnel to appear 111.111. These both will be done inside a crypto map. The problem with that is on one interface, you can only have one crypto map. Okay? So what you would do in this case is you would create one crypto map with multiple what? Sequences to define the different traffic. We'll do that later on. For right now, just understand the number 10 is just a sequence over here. Now, after the number 10, I need to define how am I generating my session key. Where am I going to get my session key from? Who's generating my session key and exchanging the session key? What protocol? Phase 1, ISACEMP, right? Diffie-Hellman is generating it and then exchanging it using phase 1. So I need to say IPsec ISACEMP, which basically tells it that I want to generate my key, my session key from ISACEMP. That links it up to where? This guy. Okay. What if, I'm not saying you should do it, what if I wanted to do the key manually? If I wanted to do key create the session key manually, I don't need ISACEMP. But how do I define that? I define that by using a keyword called manual. If I do manual over here, I don't need this. But then what I need to do over here is I need to set my session key over here. Not recommended to do that because now I'm creating a manual key for session. But then I don't need what? ISACEMP. But because I'm doing it based on ISACEMP, I'll do ISACEMP over here. I'm not going to define my session key. 99% of the time, you're going to see that. Make sense, guys? You guys understand the significance of this IPsec ISACEMP? It's not just there for the heck of it. It is the one that links it up to get the session key from ISACEMP. What's the other option? You can do it manually. There's no regeneration. You need to go manually in and reconfigure the key. And you can hire like an assistant, maybe an intern, to every hour go and set a new key. That occur? But yeah, otherwise, it's once you set it, it's set up forever. There's no timeout on it. Crypto key monkeys. There you go. No stress. All right, so what do I do inside the crypto map? 3 parameters. Every crypto map requires 3 parameters. That is true. Crypto map requires 3 parameters. What are those? The ACL, the peer. Based on this traffic, where do you want to set the tunnel towards? And once you set the tunnel, what are your parameters for this? This is your tunnel 2. This is phase 2. You've already gotten the key, so you need to set it up that this tunnel will be used for this traffic to this peer and using this transform set. These are the 3 parameters that are required over here. That's what you're tying up together. ISACEM, the transform set, and the ACL. So inside the crypto map, you're going to have match address to specify the ACL. If traffic comes in that matches ACL 101, create a tunnel towards 200.111. And over there, the transform set that you want to use is called key set, this name. So every crypto map will have this. Good so far, guys? And the last but not the least, I need to apply it. Because if I just create it, it's like creating an ACL and not actually applying the ACL. So the last thing is apply the crypto map for it to take effect on the outgoing interface. So in our case, that interface is E0/0. Crypto map CMAP. Done? You understand it? So what are the 5 steps to set up an IPsec LAN-to-LAN tunnel? Step 1, phase 1, which is your ISACEM. Step 2, phase 2, which is ESP parameters. That's a transform set. Step 3, your ACL. Step 4, link them together using what? Crypto map. What do I mean by link together? This ACL will be used when this traffic comes in, 10.1 going to 10.2, set a tunnel towards 200.111 using this transform set. Last thing, apply. Good? And that's it. Those are the 5 steps. So I can take this, go to router 1, and paste it. Phase 1, phase 2, 3, this is your 4 crypto map, and this is 5. What do I do on R2? This is what I want you guys to get used to, doing the config in Notepad, because when you do that, what I can do is copy the config and start configuring router 2 again in Notepad. This number, locally significant, whatever you want to do, this is just a priority. These parameters need to match. What parameters? Because you need to have the same key, encryption, and a hash. The only thing is, I'll change the address over here. It's towards 199. The transform set can remain the same. Even the name, again, it's locally significant. I'm just using the same name. Interesting traffic ACL, it's going to flip now because the traffic will be generated from 10.2 on router 2 towards 10.1. Link the above parameters. The only thing that I need to change over here is what? My tier address. I'm on 2 pointing towards 1 and apply it. Take a look at it. Tell me if you guys are okay with the config. Copy. Go to router 2. Paste it. Now this tunnel does not come up immediately. Why not? It needs to have some interesting traffic, trigger traffic, to bring the tunnel up. So how do I check the tunnels? There's 2 commands. For phase 1, the command is show crypto ISACamp SA. I put the full command. Notice there's nothing there. Show crypto IPsec SA. This is phase 2. No security associations. Although my ACLs are there, there's no security associations created. I'll show you when it does what it looks like. So I'll also put the verification commands for you guys. Phase 1, show crypto ISACamp SA. Phase 2, show crypto IPsec SA. SA stands for Security Association, just in case you're wondering. So now what I'll do is I'll generate some traffic. Ping 10.1.1.1, source is 10.2.2.2. This is interesting traffic. Okay, what do I have as the address over here? 10.2.2.1. There you go. Traffic gets encrypted. If I take a look at the middle router, this is my topology. Router 3 has no idea about the 10 network. It only knows about the public networks, but the packet's going across, right? You saw the ping work. Not only that, now you will notice that if I do a crypto ISACamp SA, my encryption of my phase 1 tunnel is up. And what's the status? Idle. It's done its job. It's exchanged the session key and it's sleeping right now. This is phase 1. And it is 99% of the time going to be idle. If it's idle, it's a good thing. Show crypto IPsec SA. It tells you that I have a security association done. This is the key. This is the key that I'm using. It has a key ID, actually. It's not the key, it's a key ID. I'm using the transform set of ESP SHA. That's what I specified. The key ID for my outbound key means my encryption key is 3359, which is my session key over here. I'm on 2, so this I can equate this based on our example to session key number 2. And the inbound key, the one that he's using the one that he sent me, is this key, which is 2876. This is session key number 1. That is correct. They will increment and change as well. All right. The other thing that I want you guys to take a look at over here is I have some encryption that has taken place. You guys can see that over here. 9 packets encrypted, decrypted. Understood, guys? So every time I do a ping, which is 5 packets, this number will increase. Good? Absolutely. For phase 1 as well as for phase 2. If you want to change the phase 1 parameters, it is done over here. There's a command called lifetime over here. The default lifetime for this tunnel is 86,400 seconds, which is 24 hours. That's for what? Phase 1. The default is 86,400 seconds. I told you phase 2, which is the session key parameter. This is 3,600 seconds. I can change that as well. IPsec Security Association, lifetime in seconds, and you can specify the size. This is phase 2. All good, guys? Everybody okay with this? And I put this information on your PowerPoint as well. So after this, to configure the LAN to LAN, this is phase 1. Remember these parameters? Take a look at it. Tell me if you guys are okay. For phase one, I'm doing router one, router two simultaneously. Step two, which is your phase two parameters. Step three, which is your ACL. This one has to be flipped. I'll flip it for you guys. Good. Step four, crypto map. Step five, apply. All good? All right. So what I want to do now is do a bigger topology where I have multiple tunnels. You guys are okay with this one, right? So I'll save this for you guys. And now I'll open up a newer one, a different one. Let's do this one. I have another one that I'll open up. Save as, I'll save it in a folder. I have a folder specifically for you guys. IPsec. Should I do this? IPsec multiple L2L crypto map tunnels. All right, so in this, what I want to do is I want to set up two LAN to LAN tunnels. I want to set up one over here. And I want to set up another one over here. Whichever comes first, that is correct, yes. So I want to set up two LAN to LAN tunnels. One between R1 and R2, another one between R1 and R5. Let's give them names over here. Let's call this Los Angeles. Let's call this Sydney. And let's call this London. All right. This is the LAN to LAN tunnel that I want to do on R1 to R2, R1 to R5. Okay. We'll do this and then we'll take a break. So to set this up on my Eve, I'm going to stop these routers. I also want to do this. Wait 1 second. Start up configs. Come on. 1 sec. Okay, where's that option? There you go, that's it. I'll do that later on, that's okay. And the other one that I need is this guy. This one. This is the topology that I was looking at. Fire this up. So this is the topology. R1, R2, R3. This is acting as the internet. So this is my internet in the middle. Okay. That's R6 is acting as the internet. Router 1 has 10.0 as my public network. 2 has 20.0. 5 has 50.0. Let's set up my first tunnel between R1 and R2. So this is my second lab over here. The good thing is I'm going to reuse the topology, configure a LAN-to-LAN tunnel between R1 and R2 to encrypt traffic from 10.1 to 10.2 behind the respective routers. So router 1, which is Los Angeles. Phase 1, we'll do this. The public address of the other guy is 192.20.2, which is this guy. Router 2 is 20.2. That's the public address from router 1 to reach router 2. ESP parameters, I'll keep the parameters are the same. Interesting traffic will be the same. Crypto map, I just need to change my public address and apply it. It's the same interface. So this is on LA, blank router, just with the interface configs that I had. 10.1, 192.1.10.1. 10.1 is the LAN segment. Another LAN segment is 172.16.10. So I'll base the same config that I did on R1. Just the changes are the public addresses are 20.2 based on the different destination. R2, again, 20.2 is the public address. 10.2 and 172.16.2.0 is the LAN segment. As to the configuration over here for router 2. Again, same configuration, just 0.2, 10.1. This is again 10.2 to 10.1. This is okay. 10.1, and this is my crypto map. Tell me if you guys are okay with this. I haven't changed anything over here except for the public addresses. And I'll tell you the reason I wanted to do this is I wanted to bring in the second router over there. The other topology did not have it. So copy it. Let's go to router 2 and paste it. If you guys have any confusion at any given time, please let me know. So now router 1, I can go over here and do a ping 10.1.1 sources. So I'm on 1, so 10.2.2.2 with a source of 10.1.1. And my encryption, my tunnel comes up, idle. And there you go, the associations. My traffic is encrypted. Now the main objective of doing this particular lab was second tunnel. Good, Sammy? Now, for the second tunnel, I want London to set up a tunnel towards R1. Let's do London first. This was LA and this was, what's the other city? Sydney. Now let's do London on my second tunnel. Now the third lab. This guy is up, so I can do my third lab now. Lab number 3. configure a LAN-to-LAN tunnel between R1 and R5 to encrypt traffic from 10.1 to 10.5 behind the respective routers. Take a look. I've done R1 to R2 already. Now I want to do R1 to R5. Everybody following? Now on R5, I'll do R5 first over here, which is London. I want to use the same phase 1 parameters. Okay? But my key, again, key is also going to be pointing to that. My phase 2 parameters, I want to use different ones. I want London to LA. I want to use MD5 as my phase 2. Good. I can still call it T set because I'm in London. It's my first transform set. No problems. My interesting traffic ACL will be from London, 10.5 to 10.0. London is the new router. My crypto map will still point to 10.1. This is also good, and I'll apply it. So London is done. Let's paste it. Let's check London first. Make sure it's blank. Yeah, it is. And there you go. So this is London pointing towards this guy. Now the problem over here is I already have one crypto map applied to what? This interface. Remember, I applied on E0/0 a crypto map called CMAP, which has this tunnel. On one interface, I can only have one crypto map applied. But I need to do another tunnel towards R5, which is on the same segment with different parameters. What are the different parameters? Because the phase 1 parameters are the same, I don't need to define the parameters again because it's the same parameters. If I had another set of parameters, I would put a sequence number 10 and change it. In my case, I'm using the same, so I'm going to keep it as is. I do need to define a key for 50.5, which is the public address of Sydney, R5. The transform set has changed. What did I call the transform set over here? ESP, triple des, SHA. My T set over here is called triple des MD5. So I'm going to create a T set -2, a second one, because I need this. I need to keep the T set for R1 to R2. I'm creating a new T set 2, which will have triple des and MD and SHA. First one has triple des and MD5. I need a new ACL because this ACL is going to be from where to where. Oops, sorry. This is okay. I didn't need to change this. Oh, yeah, I don't need to change this. That's all good. I have to change this one. Sorry. So London is done. I need to do Los Angeles now. So this is okay. This one needs to change. I want to do MD5 over here. Why? I want T set 2 to match the T set over here for London. So I'll create a new T set called T set 2 because I want to keep T set, the original one, for doing the tunnel towards Sydney. My crypto ACL, I need to change it to 102. Why? It's 10.1.2, 10.5, different traffic flow. Okay. So again, here, my key, I needed to define it towards 50.5. This one I changed because I required a different parameter set. If it was the same parameter set, I could have used T set. My interesting traffic, I created a new one, 10.1 to 10.5. The first one is 10.1 to 10.2. Now this crypto map, I can only apply one crypto map per interface. So here I'll say crypto map 20, a new number, which uses ACL 102, which is 10.1 to 10.5, and the peer address is 50.5. My transform set is T set 2, this parameter set. You guys understand what I'm doing? And this one, I don't need to apply. I cannot apply two crypto maps to the interface. I'll take this one out because it's already applied. So this is my second tunnel on the same interface. Second crypto map on the same interface, a different sequence number. Same name, different sequence number. Let me go ahead and do it. I'll show you how it shows up on R1 now. Copy. I'll go to router 1 and paste it. Now let's take a look at the config one step at a time. Show run. If you take a look at your policy, I have a single policy because the same policy is being used for phase 1 between R1 and R2 and between R1 and R5. I'm using the same policy, so it's okay. I need to define the key. Although it's the same key, it has different peer addresses. So I need to define the two keys. The transform sets. Notice I have two transform sets. One that is used between 1 and 2. The other one that is being used between 1 and 5. Which one is used where? In the same crypto map. When I go to 101, which is 10.1 to 10.2, I'm using key set for this destination. In the same crypto map, 20, second sequence number, which is going to be for this ACL, which is 102, 10.1 to 10.5, towards 50.5 using the transform set key set. So that's the purpose of this sequence number over here. Everybody okay with that? And then when you go to apply it, I just have one crypto map. And then the two ACLs, 10.1 to 10.5. So now I'm ready to set up what? My first tunnel is already up. 10.2.2, source is 10.1.1.1. How do I know it's up? ISACMP SA, it's up. IPsec SA, I have about, this is the second one, which is still down, which is towards 50.5. How do I know it's down? No inbound or outbound security associations because I have not done any of the traffic. Is there a way to have a single crypto map ISACM key statement for all pairs? Yes, ISACM key, you could use the address as 0000, or you can play around with the mask over here as well. Remember the address, so I can use the address as 0000. So it's down. The other one though, 10.1 to 10.2 is up. I have 9 packets encrypted. If I do another one, I should go to 14 packets. There you go. But my second tunnel is still down because I have not generated any traffic towards. Let's do that. And something is wrong. Let's check. I'll check my ACL. It is telling me that there is some traffic that was generated, 10.1 to 10.5. So my ACL is okay. The first check I do is my running config check. 50.5, which is good. TSET, ESP, MD5, which is good. 50.5. TSET 2. Yeah, I'll check that as well. That is okay. Let's check R5 now. Oh, everything was fine. I just forgot. I pasted it. I didn't press enter on the crypto map CMap command. So now, let's try it again. There you go. Boom. Show crypto ISACMP SA. Oh no, it's not up yet. Yeah, this one is the one. Now it should generate it. There you go. This will eventually be deleted. This is the one that I was going when the other guy didn't have it. So now I'm up with it for phase 1. Show crypto IPsec SA. 4 packets sent and received to 50.5. If I do another thing, another 5 packets should add. So now I have 2 tunnels going at the same time. The error that I had was I pasted the config, but on the last command, last command, press enter for it to apply the crypto map. I had not applied it. So now I have two tunnels over here on R1 of the same interface by using multiple sequence numbers in the crypto map. Everybody okay with this? This is your foundation of IPsec. This will help you for all the different IPsecs that we do, whether it's for GetVPN, DMVPN, any of that. And this is done. Let's go back over here to our thingy over here. We're done with this. Good time to take a break. Any questions before we take a break? All good?